In this video, we are going to look at scatter plots and their common features, along with correlation and how we use it to describe characteristics of scatter plots. A scatter plot is a common type of data display which is used to evaluate trends and relationships between independent and dependent quantitative variables. In other words, we are observing the association between the variables. Our independent variable, x, is used to explain or predict changes in the dependent variable, y. The independent variable x is also called the explanatory variable. Our dependent variable y is subject to influence by the variable x. The dependent variable represents what we wish to predict. In other words, we are using our independent variable x to try to make a prediction or inference about our dependent variable y. In scatter plot analysis, we look at three main features: form, direction, and strength. For form, we look to see whether our scatter plot is linear, nonlinear, or null. For the direction, we look to see whether it's positive, negative, or a combination. And when analyzing the scatter plot's strength, we look to see whether the relation appears to be strong, moderate, or weak. We also look for unusual features such as outliers. An outlier will appear as a point situated away from the overall pattern of the graph. In scatter plot analysis, we also consider correlation. Correlation is represented by lowercase r. It gives us information about the strength of the linear association between two variables, provided the following conditions have been met. The quantitative variables condition, which states that correlation only applies to quantitative, in other words, numeric variables. The straight enough condition: is the scatter plot linear in form? The outlier condition: outliers can have a major effect on correlation. If there is a significant outlier, the correlation should be reported with and without the point. Let's look at a few examples of scatter plots and analyze the correlation for each. On the top left, we have a negative linear correlation. We see that our direction is negative, the form is linear. Also, this relation appears to be very strong, with our data points scattered fairly closely about the line of best fit. A negative linear correlation tells us that as x increases, y tends to decrease. Next, let's look to the right to see a positive linear correlation. Here, the direction is positive, form is linear. Again, this correlation appears to be fairly strong, as our data points are scattered fairly closely about that regression line or line of best fit. And we can see that as x increases, our y values tend to also increase. If we look on the lower left, we have a scatter plot which has no correlation. You can see that those data points appear to be randomly dispersed about the graph. If I were to draw a regression line through the center of the graph, we can see that there doesn't appear to be any clear pattern that establishes itself. Lastly, on the lower right, we have a nonlinear correlation. There does appear to be some sort of association between the variables x and y on our graph, but as you can see, it's not linear in form. Therefore, a standard linear regression model would not be the best model to represent this data. Let's look at some of the properties of correlation. correlation R must be between -1 and +1. The sign of the correlation coefficient gives its direction. For example, if R equals -0.75, this indicates that we have a negative slope. Correlation is symmetric with respect to x and y. In other words, the correlation of x with y is the same as the correlation of y with x. Also, correlation has no units. The individual variables, x and y, will contain units in most cases. However, the correlation itself does not contain units. Also, changes in center or scale do not affect the correlation. Correlation is dependent only on z-scores. Correlation measures the strength of a linear association, which we talked about a little bit briefly already, and correlation is affected by outliers. It's important to keep in mind that a strong correlation between two variables does not always indicate that one variable is exerting influence over another. Sometimes a lurking variable is present, which affects both of the variables for which we wish to determine whether an association exists. Remember, correlation does not imply causality. Let's look at a quick example where we'll match each graph to the appropriate correlation. Let's look at number 1. R equals 0.4. So we're looking for a positive slope with a moderate to moderately weak association. We draw a line of best fit through graph B. We can see that we have some data points which are dispersed about that line of best fit, but they're not clustered tightly about it. B is our best choice for number 1. Let's look at number 2. R equals 1. Well, we know that correlation can be between negative and positive 1. A correlation of -1 indicates a perfect negative slope, and a correlation of positive 1 indicates that we have a perfect positive slope, something which almost never happens when we're working with real-world data. As you can see, A is our best fit. Now let's look at graph number 3. Graph number 3 says that we have a correlation of -0.85. That's a negative slope with a fairly strong association. Graph D is our best fit. If we look at number 4, we have a correlation of -0.5. So the slope is negative. The distribution of data points around that line of best fit is moderate, not too strong. So we'd say that E is our best choice. For number 5, a correlation of 0. In other words, absolutely no correlation whatsoever. F is our best fit. Now this one's kind of tricky. I didn't say that there was no association between the variables. Obviously, we do see a clear pattern in graph F. It's just that we don't have a linear relationship. So that's why our correlation here would be 0. Finally, we have a correlation of R equals 0.10. Very, very weak. Positive. Looks like C is our best fit. So there's a brief overview of scatter plots and correlation. Remember, when working with scatter plots, correlation does not imply causality.